Motivation: high-contrast imaging of failure in copper interconnects. The high-resolution imaging of metal interconnected structures in backend-of-line stacks in integrated circuits, ranging from several hundred nanometers to tens of nanometers, is increasingly challenging for physical failure analysis in the semiconductor industry, due to their growing complexity and density. X-ray microscopy and tomography are non-destructive techniques for the imaging of structures and defects in three-dimensional interconnected structures. However, the image contrast is often weak with commonly used photon energies, such as 5.4 keV or 8.05 keV. Selecting a photon energy just above the X-ray absorption edge of the chemical element of interest significantly enhances the contrast in X-ray imaging. In this study, imaging 3D copper nanostructures within low-K dielectrics benefits from using gallium K-alpha photons with an energy of 9.2 keV, slightly above the copper K absorption edge at 9.0 keV. The graph demonstrates a 5-fold increase in image contrast between copper and the low-K materials using gallium K-alpha radiation rather than copper K-alpha radiation, due to the sharp decline in X-ray transmission at the copper K absorption edge. Transmission X-ray microscopy setup. A laboratory full-field X-ray microscope, equipped with a liquid metal jet X-ray source with an indium-rich gallium-indium target, a glass capillary as a condenser optic to illuminate the sample, a magnifying Fresnel zone plate as an objective lens and a scintillator-coupled complementary metal oxide semiconductor camera as a detector, was used. A photon energy of 9.2 keV was used to image 3D copper interconnected structures, and it was demonstrated that the limitations for high-resolution X-ray imaging, that is, a low image contrast and long data acquisition times for high-resolution imaging, can be mitigated. Siemens star test pattern images. The imaging performance of the used transmission X-ray microscope was demonstrated at the X-ray resolution target, which possessed a Siemens star test structure with a minimal feature size of 50 nanometers, patterned into a 700 nanometers thick gold absorber. With the present setup, a total magnification of 200 times was achieved and 100 nanometers features were resolved in the radiograph on the right side. Applications in microelectronics: copper low-K structure of advanced integrated circuit. To demonstrate the advantage of using gallium K-alpha radiation to improve the image contrast for copper nanostructures that are isolated by dielectrics, images of the same sample were taken for quantitative comparison, using an X-ray microscope with an X-ray source and a rotating copper anode target, generating 8 keV photon energy. The sample structure shown in the scanning electron microscopy image consists of 12 copper lines isolated by low-K materials. It has a thickness in the beam direction of 2.2 micrometers. Applications in microelectronics: copper low-K imaging comparison at 2 different photon energies. 2 radiographs taken with the same image parameters, using copper K-alpha radiation and gallium K-alpha radiation, respectively, and the corresponding line plots of the image contrast in the radiographs, are provided. The dashed lines indicate the selected position for the line plots of the image contrast along the copper low-K interconnect stack, using 16-bit images. In the low right plot, the image contrasts using copper K-alpha and gallium K-alpha radiation are compared, and the different radiation types are indicated by red and blue colors. The image contrast in the radiographs of the copper low-K interconnect stack is significantly improved if gallium K-alpha radiation is used instead of copper K-alpha radiation. For copper metal 12, the image contrast is about 5 times higher when using gallium K-alpha radiation, compared to copper K-alpha radiation. This experimental result confirms the theoretical calculation, visualized by the contrast leap for copper at the copper K absorption edge, as shown earlier. Conclusions and outlook. In this study, the following occurred: an improvement in image contrast for advanced on-chip copper interconnects within dielectrics by a factor of about 5, compared to state-of-the-art X-ray microscopy imaging, was demonstrated. A liquid metal jet X-ray source with a gallium-containing target potentially enables the application of a higher power density to the anode, resulting in a higher X-ray flux that addresses the drawback of long data acquisition times in state-of-the-art laboratory X-ray microscopes. The use of gallium K-alpha radiation is not limited to samples from microelectronic products. It can be beneficially applied to other materials and objects with copper-containing components.